so let's pick up where we left off last time. Last time we talked about, we started talking about allylic and benzylic carbocations. And we said that in the case of both allylic and benzylic, we had to kind of understand what this meant with respect to the site, the locus of the activity. So if you have an allylic cation, like the one we showed, then the two resonance forms place positive charge on the end carbon atoms. And what that would suggest to you is that each of the end carbon atoms kind of shares a partial positive charge. And so each of those end carbon atoms should be reactive. And in fact, that's what you see. And so if you isolate the product here of sololysis and water, you end up with two products. And the ratios reflect the locus of the partial positive charge. So more positive charge on the tertiary, greater amount, less positive charge on the primary, less. Now, with benzylic cation, it's a little bit different because in the case of benzylic cation, reaction only will take place at the benzylic carbon atom because if anything else happens, you lose the aromatic ring. So in other words, if you've got attack of the nucleophile at either of these two carbon atoms, then the product would not be aromatic. And so for benzylic cases, it's very simple. The reaction will only take place at the benzylic site. Okay, so this, none of this is really in any way surprising. It all kind of makes sense based on our earlier discussion of resonance and also carbocation stabilization. So we can extend the discussion now to radicals. And it's going to look exactly the same, right? Because because of resonance, an allylic radical, other things being equal, is going to be more stable than a non-allylic radical. And so the example you always look at is something like 2-pentene. And so here you have an allylic site at the end, and here you have at the other end a non-allylic site. Well, the prediction you make is that removal of the allylic proton is going to be easier than the non-allylic one because the radical, when you pull the allylic one, it's going to be an allylic radical, whereas here it's just a primary radical. And that's actually reflected in a fairly large difference in bond dissociation energies. Why should the bond dissociation energies reflect the stability of the product? It's something you already know. That is that as you start to break that carbon-hydrogen bond, homolytically to get a hydrogen radical and a carbon radical. As that process starts, you start to experience the stabilization of the radical. And so you see this very large difference in bond dissociation energies between allylic and non-allylic hydrogens. And so given that large difference, if there's a choice of making either a radical that is allylic or one that's not allylic, always the allylic one will win out, and that's the one you're going to get. The situation with benzylic and non-benzylic radicals is entirely the same, right? So if you have two sites where radical reaction can take place, you'll always see the benzylic site. And so, for example, with bromination, you can do just free radical bromination, something we've seen many times in Chem 272. And let's go through it again. So this one is a radical change. So the bromine-bromine bond is weak enough that either by shining a little bit of UV light on it or by heating it up, you end up dissociating the bromine into bromine atoms. The propagation steps are hydrogen atom abstraction to form a benzylic radical, and then the benzylic radical reacting not with a bromine radical, that would be what? That would be a termination step, but reacting with a bromine molecule to form the benzylic bromide and to regenerate the bromine atom that then can enter the cycle a second time. So this is the same kind of radical chain mechanism that you remember from Chem 272. I hope you remember. Any two radicals combining is going to represent a what? That's going to represent a termination step. And so initiation is where you form the two initial radicals, and then propagation steps. This is the chain where you start with a bromine atom and you end up with a bromine atom. Now, notice that the hydrogen atom abstraction took place only to give the tertiary benzylic radical. In other words, you could have thought, well, you know, how come the bromine didn't pull off one of these methyl hydrogens? After all, there's 6 of them, and only one of the benzylics. And the answer to that is the bond dissociation energies. That costs, you know, more than 10 kcals per mole more to do, and so the lower energy pathway is the one that I've shown to generate the more stable benzylic radical. Now, this is all good and well with respect to benzylic bromination. The reason for that is because there's no competition. In other words, remember that if I have bromine in a benzene ring, no reaction takes place until and unless I add a catalyst. So if I add iron bromide or iron chloride or aluminum chloride or some strong Lewis acid, then yes, I will get electrophilic aromatic substitution and for a different mechanism, the one that we saw in the preceding chapter, and I will get ring bromination. And because this isopropyl group is orthoparadirecting, I'll end up with a parabromo. But I don't need to worry about that. Why? Because there's no catalyst. I'm just using bromine. There's no iron bromide, there's no nothing. The situation is very different when you start looking at allylic bromination. So we know already that bromine requires no catalyst to do an addition to cyclohexene. So if I throw cyclohexene in with bromine, then the question is, well, gee, what's going to happen? Is Chem272 chemistry going to take over, and we're going to get a bisphenol dibromide that goes to a bromoniamide and therefore gives me the trans dibromide? Or maybe now we're in Chem273, so we don't need to worry about that. No, you do still need to worry about it. Now, so the question is, you know, does it go through allylic bromination, like so, or do you get ionic bromination, the way we learned before? And the answer to you know, which does it do depends on what? On reaction conditions. And so you can favor the ionic mechanism very easily. You just wrap your reaction vessel with aluminum foil to keep it dark. Why do you want to keep it dark? Well, because you know that UV light will dissociate bromine into atoms and will initiate the radical reaction. So you wrap the reaction vessel in foil, keep it nice and dark. No light gets in there, no bromine atoms. You don't heat it up, and very critically, you use a high concentration of bromine, typically in a polar solvent. A polar solvent is for what? Well, to stabilize the formation of the bromonium ion. Remember, the bromonium ion, OEM, is a cation. And so it will be formed more easily in polar solvents. For the radical reaction, you don't need a polar solvent because the radicals don't have charge separation. They don't have positive charge and negative charge in the radical reaction. So those reactions are going to be insensitive largely to polar effects of the solvent. So if I want to get the radical process, now I've got to do something different. I've got to shine light on the reaction vessel to initiate it, and I use a non-polar solvent, not because that favors the radical, but because it disfavors the ionic process, okay? Now, there's one other thing you can do, and this is maybe not obvious, and that is use a low concentration of Br2. And so why should the concentration of Br2 be important? The reason why the concentration of the bromine is important is because in the rate limiting step for the ionic reaction, you have the concentration of the alkene and the concentration of the bromine. So it's a bimolecular, it has a second order kinetics. In other words, the rate depends on two concentrations, concentration of alkene and concentration of bromine. That's because in the rate determining step, for the ionic reaction, you have alkene and bromine coming together. That's not going to be the case for the allylic bromination. That the slow step is going to be the hydrogen atom extraction, and so you can favor the radical reaction, the allylic bromination, by keeping the concentration of bromine at all times low. Now you can say, gee, that sounds really weird, because if I keep the concentration of bromine low, then the reaction's going to be slow, isn't it? And the answer to that is, well, not necessarily. What you will do, however, is you're going to really slow down the ionic process to favor the radical reaction. Now, how do you keep the concentration of bromine low? Well, the obvious way to do it, and the way anybody would tell you to do it, really, is you have a syringe full of the bromine, and then you put it on a syringe pump, which slowly advances the plunger of the syringe, drop a few seconds, another drop a few seconds, and so on. And you can keep the concentration of the bromine low that way. That's a pain in the neck. There's a much easier way, and that is to use not bromine, Br2, but to use N-bromosuccinimide, which is this stuff, as the source of bromine atoms. And so the mechanism here is a really interesting one. Here's how it works. The nitrogen-halogen bond, that NPR bond, that's a weak bond. And so you don't need a separate initiator. You can homolytically cleave that bond with light or with heat, and so you can end up initiating the reaction in the normal way to get these two radicals. So the initiation doesn't require some separate reagent. This can act as the initiator. Now, once you have this small concentration, remember this doesn't happen to all the NBS that's present all at once. A little bit of it reacts, get a little bit of bromine atom. So the bromine atom now starts the same process by pulling off the allylic hydrogen atom. Why does it pull off the allylic hydrogen atom when there are so many more hydrogens that are non-allylic? The answer is the same one, because pulling off the allylic hydrogen atom costs you roughly 10 kcals per mole less energy. So that's the fast process. Now, once you get this allylic radical, a strange thing happens. The non-radical product is HBr. Now, the HBr reacts with this stuff, and it gives you succinimide and bromine. This is not, by the way, this is not a radical step. This is an ionic mechanism. And so how does that work? Well, I can show you how it works. I mean, since you're probably curious. So we're talking about this second step, right? So here's how it works. If I have HBr and I have a molecule like this, what's going to happen? You have H plus Br minus. What's likely to happen? Well, you know what's going to happen. You have electron pairs, and so you're going to protonate the NBS. And what that's going to give you is this cation. And now bromide can come in and do this chemistry. And what that gives you is Br2 as one product, and then the double bond to OH there. That looks like an enol. In fact, it is an enol. It's the enol of an imide, and that gives rise, after proton transfers, back to succinimide. So that's the mechanism for this step here. Now that's not a radical reaction. This is an ionic step, right? So I've indicated that. But what it does is it liberates a small amount of Br2. And so now this can react with Br2, give you the allylic bromide, and regenerate the bromine atom that can enter the chain again. So this is a little bit of a different mechanism. It's still a chain reaction, but notice that one of the reactions in the chain is actually not a radical reaction. It's an ionic step. So notice that this ensures that you end up with a very low concentration of bromine. Because the only time you get bromine is when you get a radical. The only time you get this radical is when you've had an initiation, when you go through the cycle. So you never generate lots of bromine unless you're generating this first step, unless you're doing this first step. So that keeps the bromine concentration low. And then there's another trick you're playing in this reaction. That is, the reaction is done in carbon tetrachloride. And that turns out to be a critical solvent for this reaction because NBS is hardly soluble in carbon tet. And so it's a heterogeneous reaction. That means that you never get a huge amount of NBS in solution, and therefore the reaction initiates slowly too. So it all comes together really nicely. Now, what's the problem with this? The problem with this is carbon tet. Carbon tetrachloride is kind of a verboten item in the labs these days. In fact, I kind of think that we're not allowed to manufacture it anymore. And so the only carbon tet that you can find is stuff that was manufactured a long time ago. There are you can substitute it for other things, but it's kind of an item that people like to hoard. Why is that? Well, for one thing, it's toxic. So it's volatile and it's toxic, which is kind of a bad combination because you can breathe the vapor and get intoxicated or die. It turns out that if you have alcohol in your bloodstream, then your blood dissolves a heck of a lot more carbon tet than it would otherwise. And so in the bad old days, you used to be able to buy spot removers that contained carbon tetrachloride. And these were sold, for removing spots from rugs. Why does that work so well? Because most of the spots are greasy, and carbon tet does a really good job of dissolving hydrocarbons. And so, the following scenario would play out. People would die. Maybe some guy comes home, sits down, has a drink, notices that the rug looks like heck, so he gets up after having finished his drink and tries to clean it up. Of course, you're spreading carbon tet over a big area of rug, lots of vapor, alcohol in the bloodstream, and the guy, there are actually deaths from that. So, useful solvent, but toxic. Okay, so we talked about allylic and benzylic cations. We talked about allylic and benzylic radicals. So what's left? Well, obviously, allylic and benzylic carbanions. And the situation is always going to be the same, right? And so you can look at the pKa's. The pKa's give a very good indication of what goes on. If I just take ethyl, that proton there has a pK of 55 or 60. As I've told you, a number that big is completely meaningless. And so it just tells you that this is essentially, it's not acidic at all, but there's a big, big difference here. And, we're looking at almost 20 powers of 10. And so forming, getting the allylic carbanions much easier than getting the ethyl carbanion. That happens for a couple of reasons. The carbanion is resonance stabilized just the way the cation was and just the way the radical was. But there's an additional reason here, and that is the following: that if you imagine the allylic carbanion, in fact, you don't have to imagine that. I can even draw it for you. So if you have the allylic carbanion, then this, I'll put the electron here, it's got a negative charge. This carbon is going to be what? It's going to be sp2 hybridized. And so it is, because it has a higher S character, it is able to support that charge more readily, but also the adjacent carbon is sp2 hybridized. And so it will inductively remove electron density from here. And so the fact that you have an adjacent sp2 carbon also contributes to the acidity of that proton. So for these two reasons, it's easier to pull a proton off of an allylic carbon or benzylic carbon than one that is non-allylic or non-benzylic. Now, we'll never really see allylic or benzylic carbanions as such, but what we will see are benzylic and allylic Grignard reagents, benzylic and allylic organolithium reagents, and so on. These are not carbanions, they're organometallic species, but recall from Chem 272 that they react and they have properties that are equivalent to a carbanion. And so when we talk about a carbanion, and we'll be sloppy, we're going to mean an allylic Grignard or an allylic lithium species or whatnot. So when we say an allylic carbanion, that actually we're talking about this, or lithium. And so these kinds of species, Grignard reagents, react as if they are carbanions paired up with a positively charged metal. And that's, yeah, just so you know, when we say carbanions, this is really what we're talking about. Now, this is a symmetrical carbanion, right? And so if I draw the other resonance structure, it's identical. But once I have an unsymmetrical carbanion, then I can expect reactivity at both sites, right? I mean, so both carbons, both the end carbons, will share, now not a positive charge, as we saw with the carbocations, but they'll share a negative charge. So both of these carbanions, both this one and that one, this one and that one, they both share that negative charge. And so if I quench this reaction with deuterium, I'm going to end up with a mixture of deuterated compounds where the deuterium is distributed between the two reactive carbon atoms. And because this equilibrium takes place rapidly, sometimes you'll see allylic carbanions or allylic Grignards indicated with kind of a broken line here and a negative charge. What that just means is it means an average of these two structures. Now, one thing to recognize and to not confuse at all is that those two structures, the two Grignard reagents that I've shown up here, those are not resonance structures, okay? That represents an equilibrium because a resonance structure assumes that the metal is nowhere to be seen. But in fact, the metal is bonded to that carbon in this structure, and the metal is bonded here. And so these two species have different atom connectivities. If they have different atom connectivities, then we're not talking just about redistributing electrons, we're talking about moving atoms around, and that represents a chemical equilibrium, not resonance, okay? So I know it's a little bit confusing, but try to keep it straight. It actually is different. Okay, now this is our first introduction to an allylic rearrangement. In other words, I started out, let's imagine that I start out with the primary allylic bromide. I make the Grignard. Once I make the Grignard, even though I start with the primary allylic bromide, I end up with both Grignard reagents because it's allylic. And then when I allow that allylic Grignard reagent to react, it reacts at both sides. So I get a rearrangement. And so it doesn't matter that I start out with a single bromide. And by the way, the situation would be exactly the same if I start out with a secondary bromide. Because once I form this Grignard reagent, it also will be in equilibrium with the primary. So that is our example of an allylic rearrangement, something we'll see again. Okay, so we wouldn't really be making a big deal out of allylic and benzylic carbons if there wasn't really a big difference in chemical reactivity. And so it turns out that for reactions that we've seen in Chem 272 even, there's really a huge difference in the way they react. So here's a non-benzylic, non-benzylic bromide, but the E2 elimination involves removal of a benzylic proton. Okay, so remember this is a beta elimination, and I have to remove the beta proton here. And so here's a non-allylic primary bromide, so benzylic, not benzylic, not allylic. Faster, slower. So removal of the benzylic proton, fast. Non-allylic, non-benzylic, slow. Here it is for a comparison of non-allylic, non-benzylic, and removal of an allylic proton. Removal of the allylic proton, fast, slow. So to see why this happens, and you probably, given our discussion so far, you probably can already see why this happens. You need to think about what's going on in the transition state. Now remember the transition state for an E2. That was trans and anti, that you have to have the proton, the beta proton on one side, the leaving group on the other, they're all coplanar and so on. So it looks sort of like this, where you have a hydrogen, carbon, carbon, bromine in the plane of the paper, and then everything else. So as the non-nucleophilic base approaches, I start to stretch this carbon-hydrogen bond. I start to stretch this carbon-bromine bond. That induces a partial negative charge there, and at the same time, I'm beginning to form this pi bond here. But you can see that there is some negative charge developing in the transition state on the benzylic carbon atom. And so just as we saw that a benzylic carbanion is stabilized relative to a non-benzylic one, so also is this benzylic transition state where I have not a full negative charge, but a partial negative charge on the benzylic carbon. There it is. This is also stabilized compared to what it would be if there was no benzene ring here. And so this whole transition state, the energy of this transition state is lower because the negative charge is partially delocalized into that aromatic ring. And so that's why you get a faster reaction here, because the transition state for removal of that proton is lower in energy than for removal of that proton. When you start to remove that proton, the negative charge there goes into the ring, nowhere to delocalize it here. And so any factor that will stabilize, that is lower the energy of any transition state, but now we're talking about the transition state from E2, any factor that lowers the energy of the transition state will make the reaction proceed more rapidly. And so what are these factors that favor an E2, that makes an E2 go faster? Well, we talk about alpha branching, right? So if I have alpha branching or beta branching, it turns out that the elimination is favored. Why is it favored by alpha branching and beta branching? Well, because you're slowing down the SN2. The SN2 is inhibited by alpha branching and by beta branching. So if you're slowing down the substitution, what's left for the molecule to do? Just the elimination. That's why it happens. And now we learn a third factor, and that is acidic beta hydrogens. So if the beta hydrogens are acidified by being either allylic or benzylic, or even, we're going to see later on, this is a special case of an allylic beta hydrogen. But think of this. This is a beta hydrogen too. There's the alpha, there's the beta carbon with respect to bromine. You can think of this as being allylic because of this ketone. But these are very acidic hydrogens, which we've seen before. Remember when we talked about enolates? And so this elimination is also a very fast one. So anything that acidifies the hydrogen that's being removed accelerates the reaction. I mean, it's kind of obvious, but we stated it anyway. Okay, so allylic and benzylic SN2 reactions are also faster. And look at the rates here for iodine displacing chloride. The reason we have the beta branch here, you can say that, this is unfair. Beta branching slows things down. Yeah, but this is beta branch too, right? So if I kind of close my eyes, forget that these are sp2 hybridized carbon atoms, these two chlorides look pretty close. What would be an even better comparison? The best comparison would have been the benzylic one to the cyclohexyl methyl. Okay, so we could have compared this one to that one, and the results would be pretty much the same. Notice that there's about 100,000 times difference in reactivity for the benzylic, non-benzylic. For the allylic, non-allylic, there's also a very large difference, not quite this big, but a large difference in rate. Now, this is also a trend that you probably sort of predicted fairly easily. And the reason is, why does this happen, you suppose? Well, you already know, right? It's because you're getting allylic benzylic stabilization in the transition state. I mean, there's nothing surprising there. So if you think about the allylic reaction, okay, so here's the allylic chloride. And I've shown sp2, sp2, and this is the carbon that was bonded to the chlorine. So the chlorine's starting to come off. The iodine is starting to displace, iodide, I minus, is starting to displace the chloride. And so in the transition state, you have sort of a partially broken bond to chlorine, a partially formed bond to iodide, I should say chlorine chloride. And so both of these atoms share some of the negative charge. But notice that the carbon atom that's undergoing chemical change is now becoming sp2 hybridized, and it can overlap through resonance with the sp2 with the pi electrons in the allylic CC bond. And so that stabilizes the transition state. It's allylic stabilization in the transition state translates into what? Into a faster reaction. Lowering the energy of the transition state, activation barrier is lower, reactions faster. Okay, so the take-home message is that anytime you have allylic or benzylic anything, expect to see faster or different reactivity, typically faster, okay? Now, we're going to see another reaction now, oxidation. We talked about oxidations fairly extensively last semester. This is kind of a special case. This is oxidation of benzylic or allylic alcohols. Now, manganese dioxide does not oxidize non-allylic alcohols, okay? So it's what's known as a very useful tool because it is a specific oxidant. That means that if I have a molecule that's got multiple hydroxy groups, but only one of them is benzylic, then I can selectively operate on that benzylic hydroxide, I can oxidize it, and I can do that with this particular reagent. So the way you do it, by the way, this is a heterogeneous reaction. What does that mean? It means that this stuff doesn't dissolve in dichloromethane, okay? So we've talked about heterogeneous reactions, right? And one of the things that I've told you is that the reactions that take place between a solid that doesn't dissolve take place on the surface of the solid, right? Because your reagent and the reactant only come together at that solid-liquid interface. And so these kinds of reactions are going to be very, very slow unless the manganese dioxide has a large surface area. In other words, if it's just a lump of manganese dioxide, then it doesn't have a very big surface area. And since the only reaction that takes place at the surface, the reaction is going to be miserably slow. And so the way you make the manganese dioxide is that you make it so it's a very fine powder. So that means that its surface to mass ratio is huge. And under those conditions, these reactions proceed at a reasonable rate, but because they are heterogeneous, they have to be stirred vigorously, okay? So you agitate. Now, how do you make this stuff? You can buy it, but actually the best stuff is the stuff you make at home. And you start out with two different sources of manganese. So you start out with a manganese manganese sulfate, which is MnSO4. And this is manganese plus 2, and potassium permanganate, permanganate, which is manganese plus 7. And you combine these, and you end up with, so 3 to 2, and you end up with 5 manganese dioxide. Now, this stuff precipitates. Potassium sulfate and sulfuric acid is water soluble, and so you end up with an aqueous solution of salt and sulfuric acid, throw that away, and then you collect this stuff. Now, notice this is kind of a strange reaction, isn't it? Because you start out with two different oxidation states, the same metal, and then they go to the same oxidation state. These reactions are known as disproportionation reactions. So, in other words, it's an internal redox process. This gets oxidized, that gets reduced. Okay, so that's how you make the manganese dioxide. What's the mechanism? Oh, by the way, you make this an aqueous solution from an aqueous medium, and after that, after you collect it, you put it in the oven and you dry it good and well. And the reason you do that is because the presence of water that might be present on the surface of the manganese dioxide strongly inhibits the oxidation. And you can kind of see why, because the first step involves addition of the hydroxy group to the manganese. So imagine protonating this oxygen and then having an electron pair go in. Okay, so you end up with this manganese ester. Here the oxidation state is 4, doesn't change, but at this point it does change because you end up with a homolytic process. You end up breaking this carbon-hydrogen bond. Hydrogen atom gets bonded to oxygen. Electron sits here as a radical, and one of these electrons from the manganese oxygen double bond, one of the electrons goes and sits on the manganese. The manganese just picked up an electron. It picked up an electron, guess what? It's at a lower oxidation state. And so this is now manganese 3. But you end up with a diradical that can cleave as shown. At this point, manganese picks up another electron and is now manganese 2. And of course, this carbon atom got oxidized. So manganese got reduced by 2 electrons, that carbon got oxidized by 2 electrons. So it's a 2-electron oxidation that takes place. Remember that when something gets oxidized, something else has to get reduced. So if the carbon is getting oxidized from alcohol to carbonyl, then the metal has to be reduced. And in fact it is. It goes from 4 to oxidation state 2. Now why is water bad? Well, look at that first step. If I close my eyes and I don't think about this alkyl group, that looks like water. So water can compete for the manganese dioxide to give you a hydrate here, and that's no good because that's going to inhibit this first step. And so that's why the reaction has to be done under strictly anhydrous conditions, or it takes forever. So look at how this mechanism goes. You get kind of an ionic reaction here, and then the rest are radical steps that generate your double bond and reduce the manganese. This mechanism is not that different from some of the other oxidation mechanisms that we discussed in Chem 272. Now, okay, so, and by the way, this works for benzoic, it works for allylic, doesn't work for anything else. You can also trick this reaction. You can use this to form a carboxylic acid. It's kind of neat. Let me show you how you do that. So remember, the manganese dioxide only oxidizes allylic alcohols, right? And so you know that you can oxidize an aldehyde to an acid, but that happens with chromium trioxide when there's water present. Remember we talked about that. So we said that you start out with an aldehyde and there's water, that you end up getting a hydrate. And now the hydrate looks like an alcohol, and this can be oxidized by chromium-6 to give you a carboxylic acid. Okay, so for the allylic case, this is more or less how you do it. So this won't, no reaction with manganese dioxide. Why? Because I don't have an allylic alcohol. However, if I use a stoichiometric amount of cyanide, what happens? Well, cyanide is a good nucleophile, and so let's just say HCN, right? So I protonate this, and I get cyanide adding. Actually, equilibrium strongly favors the product, and so I end up with what's known as a cyanohydrin. But guess what? This is an allylic alcohol, isn't it? And so this will oxidize with manganese dioxide to give you an acyl cyanide with water, as we will see. This gives you the carboxylic acid. And so there are little tricks you can play like that if you know the mechanism to get around the limitations of a reagent like manganese dioxide. Now, there's another oxidation that we need to talk about, We're not going to talk about the mechanism. The mechanism is very complex. This is an oxidative cleavage. So it means when you say oxidative cleavage, where have we seen oxidative cleavage? We've seen two of them. In Chem 272. Yeah, ozanolysis is the one you should all remember. And then there's another one, that's the periodic acid cleavage of a diol. Both of these are oxidative cleavages in the sense that you cleave a carbon-carbon bond and you end up oxidizing the two carbon atoms as well. Well, okay, so here's another oxidative cleavage. The cleavage here takes place at the benzylic carbon. And it will take place if you have a methyl, an ethyl, or an isopropyl, but you need to have at least one benzylic hydrogen atom. So the reaction gets started at the benzylic hydrogen. If you don't have a benzylic hydrogen, no reaction. So T-butylbenzene is inert. But if you use hot permanganate or hot chromium trioxide, really vigorous conditions, then you end up oxidizing this all the way to the carboxylic acid. If there's another carbon, this gets cleaved. If there are two carbons, then these methyls get cleaved, and so on. And so, but in all cases, you end up with the carboxylic acid, the benzoic acid. So any kind of aromatic alkyl that has at least one benzylic hydrogen always gives rise to carboxylic acid. Turns out to be fairly useful to do. Now I can say that, gee, that just seems kind of weird because, we know that I can take a benzylic alcohol like that, I can treat it with chromium trioxide and get a ketone. And we know that chromium trioxide reacts with alcohols to give aldehydes or ketones. Since when does it give carboxylic acid? Well, it turns out it gives carboxylic acids when you heat it up. So if you take this and heat it with chromium trioxide, presumably it goes through something like this, but it will eventually give you the carboxylic acid as well. Okay, so this is kind of the summary of benzylic and allylic reactivity. Before we talk about terpenes, I noticed the new edition of Loudon has a little chapter on cytochrome P450s and metabolism. So what are cytochrome P450s and why do we care? Cytochromes are enzymes that are in our liver. And as you probably know, liver and kidney are the two organs that are most responsible for detoxifying things and for metabolizing things. And so if you're testing a new drug on poor little mice or rats, then you want to test for toxicity. One of the tests that they do is after dosing the animals with whatever drug you're testing, they sacrifice them. That's the euphemism for kill them. And then they dissect out the liver and they weigh it. So you try to see whether the liver is enlarged. If you have an enlarged liver in the animal, then what that tells you is that the drug was toxic and the liver was gearing up to make lots more cytochrome P450s. And so what these enzymes are, by the way, there's a whole bunch of these. But all of these enzymes have at their business end, so to speak, at their working end, they have an iron atom. The iron is in a weird oxidation state. So I'm not going to show the protoporphyrin. So you have a big protein, which is made of amino acids. Then it has an active site, which is a protoporphyrin. Take a look at the structure. It's too big to draw here. And in the protoporphyrin sits an iron that's in its +5 oxidation state. And so we'll pick up on this discussion on Monday. Now, okay, I guess I can tell you the exam will cover material that's covered until the end of not today's lecture, but Wednesday's lecture. Okay, so anything that we cover up to Wednesday is fair game for the exam.